In this video, we look at work. Right, so in physics, work is related to a force on an object. Specifically, when a force moves an object, we say the force does work on the object. In other words, right, what this means is work is the energy required to move an object. Let's say we have an object. We exert a constant force F on it to move it a distance d. The work done in this case the work performed is work equals force times the distance. All right, so force is generally measured in the Newton. Distance generally will be measured in the meter. So the standard unit for work is the joule. All right, and the joule is the Newton meter. In the English system, unit of force is the pound, unit of distance is foot, and so the unit of work would be the foot-pound. However, it is very rare that a force applied is constant. So what we do now, suppose we have a force F of x that varies with x. And this force moves an object in a positive direction along the x-axis. Right? And it moves from the point x equals a to the point x equals b. In order to calculate the work, we partition the interval AB into n subintervals of equal length. call that length delta x, which is b minus a divided by n. We are now going to consider the ith subinterval, x I minus 1 to xi. Furthermore, we're going to let the force applied over this interval be f of x sub I. Right? Now, we're assuming this because if delta x is small enough, we can treat the force along that tiny interval as a constant. Therefore, the work over this interval, w sub I, is just f of xi times delta x. This obviously means the total work done would be the sum of these, which is approximately the sum as I goes from 1 to n, f of x sub I times delta x. As the number of subintervals increase, our approximation gets better. This is a Riemann sum. So therefore, we get the following. So the work performed in moving an object along the x-axis from A to B by applying a force f of x is given by the integral from A to B of f of x dx. We're now going to take a look at a law from physics known as Hooke's law. And this is to deal with springs. Okay, so I want 3 diagrams. If we look at the first, our first diagram is going to look something like this. No, that's not what I wanted. It's still not what I wanted. There. And so the spring is attached to some object. We refer to this line as x equals 0. And that's the first case. Second case. It'll be something like this. In this case, notice we say x is less than 0. And our third case, and we notice that x is larger than 0. When the spring is neither compressed nor elongated, right? So it's just there. We call it equilibrium length. So in this first case, we say the spring is at equilibrium. This is compressed. And then we have stretched or elongated. When a spring is at equilibrium, we say that the spring is at its natural length. Right, so we treat the length of a spring, the natural length of a spring, as the length when it is in equilibrium. Right, obviously, if the spring is being compressed, we take x to be less than 0. When it's elongated, we take x to be larger than 0. Now, here's what Hooke's law says. When the spring is stretched or compressed, from equilibrium, and I realize I'm spelling equilibrium wrong this whole time. It exerts a restoring force f of x equals k times x. In the opposite direction. Right, in other words, if you're compressing it, right, as in here, then the restoring force would be in this direction. If you're elongating it, the restoring force would be in that direction. So, compressing it, the restoring force wants to elongate it back to equilibrium. When you're elongating it, the restoring force wants to compress it back to equilibrium. Right, and here, K is the spring constant. The spring constant can only be found through experimentation, and each spring has its own unique constant. So let's suppose that it takes 10 newtons to compress a spring 0.2 meters from equilibrium. Want to determine how much work is done to stretch the spring 0.5 meters from equilibrium. Right. Well, the first thing you have to do is determine the spring constant, right? So recall that f of x is k times x. So what we're going to get is we're going to get 10 newtons is equal to k times negative 0.2 meters. And we're compressing, so the force is negative. So this means that k itself would be 10 newtons over 0.2 meters, which is 50 Newton inverse meters. All right, so our f of x, our spring constant is 50, so we get 50x. Then the work performed to elongate by half a meter, right? It's going to be the integral from 0 to 0.5 of 50x dx. This is 25x squared, evaluated as x goes from 0 to 0.5. 0.5 squared is a quarter, so we want a quarter of 25, which is 6.25 joules. Now let's compute the work against gravity required to build a concrete column of height 5 meters and square base of side 2 meters. We're going to assume concrete has a density of 1,500 kilograms per cubic meter. All right, so let's start by getting a rough sketch know, something like that. That should be good enough. All right, what do we know? We know that this is 2 meters. This is 2 meters. This is 5 meters. All right, so what we want to do is divide this up into slabs. And each slab will have equal width. Right, let's call it delta y. So if we take a look at just one of these slabs, obviously the slab is going to be square. And it's going to have a specific width. Two meters, the width is delta y. The force to move the ith slab is mass of the ith slab times g. Well, if we look at the mass of the ith slab, that would just be the density times its volume. Well, its volume is area of the base times its width. And the area is a fixed 4 square meters. Now we know rho, which I'm going to deal with later. I'll just keep it as rho for now. So combining all that, we get the force required on the ith object would be 4 rho g times delta y sub I. Now we're keeping delta y constant. Thus, our work can be approximated as the sum I equals 1 to n of 4 rho g delta y times y, right, because the distance we're traveling is y sub I, times delta y. Right, obviously that means that the work done is this limit as n goes to infinity. But that is an integral, so we get the integral of 4 rho g, or 4 rho g times the integral of y dy, and we go from a height of 0 to a height of 5 meters. So we get 2 rho g y squared as y goes from 0 to 5. Right, y squared, so 5 squared is 25. We get 50 times rho times g. If we now plug in approximations for rho and g, right, so we're taking rho to be 1500 kilograms per cubic meter. We take g as approximately 9.8 meters per second. We get that this is approximately 735,000 joules. And I'm just going to write down what we used. Now, the Earth exerts a gravitational pull or a gravitational force of magnitude F equals big G m sub e little m all over r squared on an object of mass m at a distance little r from the center of the Earth. We want to do two things. We first want to find the work required to move an object infinitely far from Earth. Then we will use this to determine the escape velocity on Earth's surface. Right, well, first for work. Right, well, it's the integral of f dr. Now, for the limits of integration, if we're on the surface of the Earth, right, we're not at 0, right? Our lower limit would be the radius of the Earth, right? And obviously we go to infinity. So to see this, think of this sphere as the Earth, right? This is the center. Well, the surface of the Earth would be located right here, right? There's a surface. So that is a distance r sub e, right? Because remember, little r measures distance from the center. Well, g is a constant. It's the universal gravitational constant. The mass of the Earth is a constant. The mass of our object is constant. So this is what we're left with. So this will give us negative G MEM all over R. R goes from the radius of the Earth to infinity. Right now, this doesn't make any sense. We should be taking a limit, right? So we're going to do that now. Let's say this is the limit as b goes to infinity of negative G MEM over R as R goes from RE to infinity. So we get negative limit as b goes to infinity of G MEM. I'm sorry, that infinity there should be a b over b minus G MEM over RE. Well, that first term goes to 0, so we're left with G MEM over RE. This is the work required to move an object infinitely far. Now, if we take approximate values, so if we take the mass of the Earth to be approximately 5.98 times 10 to the 24th kilograms, we take the radius of the Earth to be about 6.37 times 10 to the 6th meters, and we take the universal gravitational constant to be about 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Then we get an approximate value of 6.26 times 10 to the 7th joules. I'm sorry, no. Times the mass of the object, little m, right? Newton meter per kilogram. And so it all depends on the mass of the object. To determine escape velocity, we're going to use conservation of energy. For this problem, what it's going to state is that an object launched with velocity v0 will escape gravitational field if its kinetic energy is at least as large as the work required to move it infinitely far. In other words, kinetic energy has to be greater than or equal to work to move it infinitely far. Let's call it W sub infinity. This means kinetic energy, which is 1/2 m v0 squared, is greater than or equal to G MEM over RE. Right? So divide by a half m, we get V naught squared has to be greater than or equal to 2me over RE. This implies that V naught would have to be greater than or equal to the square root of 2me over RE. Escape velocity is the minimum required velocity. Thus, we get the escape velocity is equal to the square root 2me over RE. Now, this is the escape velocity on Earth. Again, if we use our values up here, we find that this is approximately 11,189.3 meter per second. Now, keep in mind, you may think this is fast, but we have already achieved it, right? We've already launched rockets into space. Well, those rockets escaped Earth, so those rockets were going at least 11,189.3 meters per second. And when you put it into perspective, in terms of the speed of light, this is extremely slow.